Welcome and thank you for joining, everyone. My name is Mihaela Blendea. I'm a principal program manager in SQL Server team. I'm very excited for this session today on Microsoft SQL Server Big Data Clusters on Red Hat OpenShift. The solutions I'm going to present today leverage the latest technologies and innovations when it comes to best-in-class relational workloads with SQL Server that is now running side by side with a big data stack, with HDFS and Spark, all on top of Kubernetes orchestrated containers. First, in case we did not meet before, just a few words about me. I have been in the SQL Server team for many years. I worked on SQL Server tools, on SQL Azure. I also work on SQL Server on Linux. I'm happy to say that I had the opportunity to work on multiple features across SQL Server stack, and for the past couple of years my focus was on SQL Server running in containers. More recently, I joined the team that helped bringing SQL Server and big data cluster capabilities on top of Kubernetes. Now let's see what I'm gonna talk about today. I will start by setting some context and go through today's landscape when it comes to collecting and making use of big data. This will serve hopefully as a good introduction for the solutions that I'm going to talk about further in the session. Solutions that are of course implemented using SQL Server, Big Data Clusters, and OpenShift. Then I will show how these technologies solve some of the challenges organizations face today when it comes to analyzing their data in a scalable and secure manner. Before we dive into the content, just a reminder that my colleagues and I are also monitoring the Q&A chat throughout the entire session, so please don't wait until the end of the session to post your questions or any feedback that you might have. But do listen to the content. There is a quiz at the end. Joking aside, we have a lot to cover, so I'll just get started. We will start with a well-known fact. For the past few years, organizations around the world started collecting enormous amounts of data. Everyone has been doing so for a while and at a scale that is continuously growing as well. At the same time, data has no value if it's just sitting around unused. It is obviously a waste. So organizations also need to do something with that data and extract value from it. First, let's talk about where is all this data coming from. So on one side, a reason that we have more data is that we have a way to store it efficiently in more and more diverse data sources and locations. And we have also made it cheaper and easier to do that with new technologies. Both the data volume and the data processing are easier and more accessible now. In today's technological landscape, scaling resources like CPU or disk does not require very costly investments. Then there is the actual data in various formats and stored in different locations, as I said, based on its type, the location where it is produced, and so on. To take a simple example that we encounter in the day-to-day life, think about when you are visiting your favorite restaurant and what happens during that entire visit. From the time you look at the order until you pay, all kinds of data is shared and collected. From personal information, your preferences, maybe even the TV show that was on at the time, till the stock price of the producers whose ingredients they are going to use to prepare your meal. From big to small, every company has big data, and they must think about the optimal solutions to store, to access, and analyze it. Also, with ever-increasing sources of data, organizations need to find solutions to store and analyze multiple and diverse sources of data that is stored in various formats. So there aren't too many enterprises out there that do not have implemented OLTP systems, historical tracking with BR reporting on top, or systems that are collecting signals from IoT devices, like sensor data from medical trackers, for example. Departments within the organization have their own data to store and access. They have data marts, and the examples can continue. So it is more obvious each day that not keeping up with taking advantage of the technology innovation in the big data space and transforming that data into meaningful insights will be a competitive disadvantage that companies obviously want to avoid. Now, we agree that once they have all this data, companies most likely want to use it. They do not want to just sit on it. They want to extract intelligence and take business decisions based on that data. So here are some just few of the examples of common use cases that we encounter based on our customer engagements. To take the example of healthcare, a very popular topic, especially during current challenging times, there are multiple use cases that organizations in this space are dealing with. From OLTP resourcing for patient tracking to BI analytics for materials resourcing and allocation, data warehousing and machine learning for revenue projection, just to name a few. But going into more details, for each type of persona involved in all these use cases, let's look at what the line of business person would like to do when they interact with these analytic systems. They want to be able to run, obviously, standard OLTP type work, like standard transactional work, but they would like also to do historical analysis over that data. But not only that, the data scientist wants to use all of this data to create experiments and then deploy a model. Maybe in this case, it's a length of stay analysis. And then the management would like a very simple interface that is very secure to be able to do predictive work, like that length of stay that I mentioned, to know exactly how long a patient will be around. The length of stay analysis also has a deep advanced analytics aspect to it, and the analytic solution that they are using must enable this type of capabilities. We are going to talk about the specific use case of length of stay in more details later, but now let's look at another very popular use case, and we're going to tackle the financial technology now, the insurance, the banks, credit unions, and the sorts. In this case, the IT department wants to be able to follow standard DevOps practices, drive everything with files from GitHub, and they also want to be able to deploy on premises or in the cloud, and they want full control over that system. The data engineers on the other side wants to bring data into the system from point of sales systems all around the world every second. Then they need to ingest that data quickly, as I said, and they also need to follow up with a step where they prepare that data for analysis. Next, the line of business operator has the same as we talked about in the healthcare case. They have OLTP or transactional needs, as well as historical analysis needs. And the data scientist wants to create models from all that data and push it all the way out to the end, to the customer. So the person that sits at the register can easily figure out in real time if a certain credit card transaction might be fraudulent. These are not the only examples. There are several others, but the same pattern applies for all the scenarios you see here. One can easily extrapolate same concepts into these examples related to government or retail industry. Based on that, we can define some of the requirements that the building blocks of an analytic solution must meet to make all these things happen. First, a secure computing infrastructure that is scalable is fundamental from platform perspective. We will explore security in more details today, but I would like to also mention the importance of manageability, storage, and networking abstractions when it comes to a solid and reliable infrastructure. Containers and Kubernetes are in the center of this architecture. They give you the choice of the software you want to run without infrastructure dependencies, so the user maintains this level of control they want that we talked about earlier. They also enable easy sharing of the software, automation, versioning, immutability, and ease of portability across various types of infrastructure, no matter if it's physical, virtual, public, or private clouds, and so on. Then you need a data platform that you can deploy on top of that and leverage the platform capabilities in terms of scale. Not only this, but the data platform must also enable the right tools and capabilities to reach out to all the data and easily build intelligent applications on top of it. We want to combine not just relational data, but also non-relational data. We want to be able to do hybrid transaction processing, not just OLTP or transaction processing. And not less important, we also want to be able to do processing for analytics. And for the data scientists, of course, the data platform needs to enable them to easily do prediction models and other specific activities. And to do all this for large-scale systems, we need to be able to put compute over the data. Let's see how all this become reality with Red Hat OpenShift and SQL Server Big Data clusters. On the infrastructure side, Red Hat OpenShift provides a commercially supported distribution of Kubernetes. So with OpenShift, you will get the clustering services you need built on the industry standard enabled by the Kubernetes platform that is very easy to manage and monitor. It is available on premises, in the cloud, and even on multiple clouds. And this is all built on Red Hat Enterprise Linux. More, with OpenShift, you get a standard vendor you can use for support that you can trust, and they are used in production systems in enterprises around the world. So from platform perspective, everything is taken care of. Now we need to take a look at the data side. When we look at all these requirements and user expectations from a typical analytic solution, we think that SQL Server Big Data Clusters and OpenShift provide a comprehensive set of capabilities that check all these boxes. SQL Server Big Data Clusters is a feature released with SQL Server 2019 that extends SQL Server's capabilities with regard to analytics workloads. And it is doing this by adding Apache Spark and HDFS to create this single, secure, and unified data platform. Big data cluster applications run as Linux containers only that are orchestrated by Kubernetes and can be deployed on premises or in the cloud. We announced support for SQL Server Big Data Clusters deployments on OpenShift earlier this year. This was a very important milestone for us as it unblocked multiple enterprise deployments that standardized on OpenShift from infrastructure perspective. An important aspect to mention here is that BDC is supported on OpenShift environments on premises or in the public cloud with Azure Red Hat OpenShift. SQL Server team worked in close partnership with Red Hat OpenShift teams and collaborated throughout the project on the design or the security capabilities that we're discussing today in this session. The outcome is that now you can build your analytic solutions on top of a fully supported stack using big data clusters with deployment best practices and enterprise-grade security guidelines that are core to OpenShift. Keeping all this infrastructure and solution requirements in mind, let's now see how SQL Server Big Data Clusters builds on top of that and what are some of its main components. You will see this in the deployment demo in just a few minutes when you issue a simple create command using our CLI tool AZData. We first lay out the controller. This component is the management service for the entire big data cluster. It interacts directly with Kubernetes APIs and deploys all the other services and applications that are part of this comprehensive solution that we call SQL Server Big Data Clusters. One of these services is SQL Server Master Instance that you can use like it's just a regular everyday SQL Server because, in fact, it is. This is the same engine that is the OLTP standard around the world, the same engine that is available on other platforms like on Windows or Linux or in the cloud, that includes all the enhancements that were released in the past years with the same performance and security guarantees. This SQL Server can do both analytics and operational workloads, but also has some additional capabilities that are specific to big data clusters deployments. For example, it has built-in automated HA with contained availability groups. Contained AGs are only available as a feature in SQL Server when deployed within BDC. Much of the additional manageability overhead required to set up and configure availability groups is taken care of by the platform, and it is all built in. From setting up the availability group, adding the master and MSDB system databases to the AG, adding a user database to the AG automatically, orchestrated upgrade, and so on. With contained availability groups in BDC, since the master and MSDB databases are part of the availability group, you don't need to manually replicate your logins or SQL Server agent jobs to all the replicas, so they are available in case of a failover. Features like read-only secondary replicas and secondary listener endpoint are already configured as well, ready for you to use to scale out and load balance your read workloads across the secondary replicas. Very important also to mention is that this SQL Server has the same data virtualization capabilities as when deployed on Windows or Linux outside of BDC. As I've mentioned earlier, organizations these days have a diverse data estate, so it is very likely that in addition to data stored within BDC, in SQL Server, or in HDFS, as we're going to see shortly, some data might reside in other systems like Oracle, MongoDB, or other HDFS systems, or Azure in SQL database. By leveraging data virtualization capabilities, you can keep the data in place and secure with less maintenance and storage cost, and access all these diverse data sources through SQL Server that becomes like this data hub. So no data is moved, only the result set is returned at query runtime. But when we think about data scientists and data engineers, their use cases are slightly different, and they want to run their workloads in a slightly different way. So that's why when you deploy a big data cluster, you're not only deploying SQL Server for OLAP and relational data workloads. The interesting thing with big data cluster is that we now included Spark and HDFS storage as this unit in the same single deployment pattern, so you can store and analyze non-relational data on this system as well. So what we call the storage pool now includes HDFS. We've also contributed to the HDFS Hadoop project with a concept called HDFS tiering, which allows you to mount other object stores like S3 endpoints, Azure Data Lake Gen 2, and other HDFS stores into the internal BDC HDFS as mount points. Then you can essentially cache it within the storage pool in BDC. This enables you to easily integrate with already existing data lakes without the need to move all the data in and out in order to get value out of it. Side by side with HDFS in the storage pool is Apache Spark. The Spark compute engine enables data engineers and data scientists to process and analyze high-volume data in scalable and distributed manner using this in-memory compute layer. They most commonly use this layer for data preparation tasks, but they can query the data lake in real time as well, and they can also leverage Spark for its streaming or machine learning capabilities. Further along, both for data sources within BDC, like the storage pool or data pool, as well as for these external data sources that we mentioned earlier, the SQL Server instance has also the ability to do scale-out queries. This means that the compute power of the SQL engine is scaled out when accessing the data lake internally or outside of BDC. And this is what we call the compute pool. You can also use scaling capabilities to store data in a set of distributed ephemeral tables for query acceleration using SQL Server instances that are part of what we call data pool. So all these additional layers enable accelerated query performance when applications are accessing data stored in the lake. So to summarize, you can query your data lake in real time with SQL, but also with Spark. You can ingest streams of data with Spark streaming. You can do training of ML models using Spark ML, but you can also build and consume models into the database with SQL ML services. And this is where this user-defined application pool is coming into the picture. You can deploy these ML models, operationalize them, and expose them through simple REST APIs that the application can easily call, all in the same security boundaries of BDC and side by side with where the data is, keeping things not only secure, but also efficient. Let's go through an actual example to make all these things real. Hopefully, this will better illustrate the use case for each of the components in BDC. For this, we're going to bring back one of the healthcare use cases we talked about earlier, the length of stay. Just to set some context on what we mean by length of stay, here is how it is usually defined. So for hospitals to optimize resource allocation, it is important to predict how long a newly admitted patient will stay in the hospital. Advanced length of stay prediction at the time of the admission can enhance the quality of care, improve efficiency, and help with accurate planning for the patient discharges, and reduce cost in general. So what needs to happen to implement this solution? So first, the hospital IT department will acquire and set up the OpenShift infrastructure. This will ensure a consistent and reliable system that is easy to deploy and it is secure. Let's assume this is deployed in the cloud, as in the demo example that we'll show shortly. Then, with a simple command and making use of a couple of manifest files that describe the layout of the cluster, like the scale, the network settings, security, and so on, the IT department deploys BDC to meet their business, operational, and analytical workload needs. So to continue our example, the line of business person, let's assume it is the hospital administrator, they use this system to run their OLTP type workloads. At the same time, they are also able to leverage the same system to see certain type of reports that require access to patient records. For example, such a report can reflect some historical analysis using these patient records. The data is available for them from SQL Server, and they can easily visualize it using Power BI, for example, or any other reporting tool. Continuing our use case, this time the data scientist wants to access some of this data that sits in multiple locations with the goal to create a data model. This model will be used to make predictions about length of stay based on the available patient data. Of course, all this has a clear business need. The hospital administration would like to be able to efficiently plan for the resources they need. The data scientist implements the predictive models for the length of stay analysis, but they want to stay within the same security boundary throughout the entire process. And they can do that with BDC easily. They will either use SQL Server master instance and leverage embedded machine learning services with R or Python that are available with SQL Server in BDC. Remember, this is the same old SQL Server engine. Or they can use Spark. This is definitely most common among data scientists, especially for targeted use cases like data preparation, for example. Data scientists do the data preparation, model training, and evaluation from Azure Data Studio or their favorite IDE, and when done, their code is operationalized and deployed in an app. These applications are deployed side by side with the data in the same security boundary within the application pool in BDC and exposed through a REST API. A medical provider, let's assume is one of the department head nurses, will use a patient tracking application that is querying this REST API. This is how they see the results of length of stay and can better plan for the resources or personnel required in the upcoming period. And this is just to give you an example on how this interface might look like. The nurse will use their intake device, it can be a tablet or whatever device they have, to monitor individual patient statuses. They can track patients' health signals that are coming from various IoT devices and push this data to be stored in BDC storage. But they can also ensure they are prepared and staff is available in the following days to meet their patient-specific care requirements. And by leveraging the length of stay predictions, they can plan for the discharge of their patients, or they can determine if a patient will be discharged during a low staff time, such in weekends, for example. Moving further from the example, managing all these services that enable you to run relational and big data workloads in a secure, efficient, and scalable way, it is not at all an easy task. But with big data clusters and OpenShift, you can operationalize management and data engineering tasks in an integrated and consistent way with this modern container-based architecture built on top of this orchestrated platform. Let's talk about a few examples that illustrate this manageability benefits. First, if you are trying to deploy big data clusters, you will notice it deploys pretty quickly for an application that has multiple SQL servers side by side with Hadoop cluster and Spark. Not to mention the multiple services that are deployed to manage the BDC cluster itself for security, high availability, monitoring, and troubleshooting. Bottom line is that you can have a big data cluster set up and ready to receive data load in a matter of few minutes. Also, one of the promises of containers is that all the software required is self-contained inside those images that are pulled during the deployment. The nice thing is that once big data cluster deployment completes, you don't need to install additional software to run your SQL Server or Spark workloads or to manage the big data cluster. Then, it is easy and fast to upgrade as we release new versions of those container images. This is another thing I'm going to show you in the demo today. You can simply trigger a code upgrade using big data cluster tools, and the controller running inside the big data cluster will orchestrate a rolling upgrade of the software throughout the entire cluster. Now, let's see all this in action through the lens of a deployment and an upgrade. I will show you how BDC integrates with OpenShift, both from manageability as well as from security perspective. And for that, I will start with an end-to-end deployment workflow. What you need to do to set up to prep for the deployment, what you need to set up as prerequisites, and then show how the actual deployment works. Then I will showcase the simplicity of the upgrade process, as I was mentioning earlier. For this demo, I'm using an Azure OpenShift cluster, and this particular one has 4 worker nodes, as you can see here. The next step, now that we validated connectivity to the cluster, we will take care of the prerequisites and ensure that BDC is deployed within the right security context. For this, we will create a custom security constraint context, short is SCC. These SCCs are groups of security-related configurations for deployments on OpenShift that support secure enterprise deployments for various use cases. The custom BDC security context is based on the non-root built-in SCC that is available with OpenShift deployments, with some additional permissions required for BDC. The security white paper and our documentation have in-depth details on the security integration. So once we have our custom security context created, here is BDC SCC in the list. You see it's available together with the other SCCs. We will create the namespace that BDC is going to be deployed in. To complete the security prerequisite, we must bind the service accounts used by various BDC applications with this security context that we just created for the above created namespace only. So this way, the namespace becomes the security boundary for BDC users. Next step is to choose what configuration template to use as baseline for your deployment customizations. For a tighter integration with OpenShift, we included deployment templates with appropriate defaults for OpenShift platform out of the box with our CLI AZ data. In our case, we are using Arrow Dev Test. The neat thing about this built-in profile is that all defaults make sense for a test environment and everything is pretty much ready to go. I will just change the name of the cluster since it has to match the namespace I created earlier. But if other edits are necessary to update storage, scaling, or service-specific configurations, you can use either AZ data commands or your favorite IDE tool like VS Code to make other customizations. So before starting the actual deployment, we may not forget to set the credentials for accessing the external endpoints in the cluster, like SQL Server or Knox Gateway or the controller. So now we set the credentials and we will issue the AZ data BDC create command. And from this point on, we are hands off. All the BDC components are laid out starting with the controller, as we mentioned earlier. And then once the central management service of the cluster is up, it will take over and it will start coordinating with using Kubernetes APIs to deploy all the other BDC applications, check their status, and so on. So now the controller is up and it will move on to deploy the other services as we said earlier. For a deployment of this size, it should not take more than 10 minutes to deploy, especially if you pre-pull the Docker images from the repo to be readily available during deployment on the nodes. So fast forward, the deployment completed successfully, and I can now log into the controller to find the connectivity information for all the endpoints available for me to interact with SQL Server, Spark, the monitoring services, and all the other external endpoints that are available with the BDC deployment. Another quick example on how to leverage the power of containers and orchestration with Kubernetes and OpenShift, in this particular case, is during upgrade. You can simply trigger the upgrade using AZ Data tool, as you can see here. It's pretty straightforward, and the controller running inside a big data cluster will orchestrate a rolling upgrade of the software throughout the entire cluster. It takes care of service dependencies, it checks service health, it rolls back if necessary, and as you can see, it's again a hands-off and fast, neat experience. For some of you that are familiar with availability groups, for example, think about how carefully you need to orchestrate an upgrade for a set of SQL Server instances that are part of the AG. In this case, with BDC, everything is built in and the upgrade sequence is considering the best practices when it comes to the rolling upgrade of SQL Server master instance that are part of the contained availability group in BDC. We've seen how easy it is to deploy and upgrade big data clusters on OpenShift. Continuing on the manageability benefits theme, another important thing to mention is that a container-based architecture like the one Big Data Clusters is using is also predictable, self-contained, and ensures a fast deployment workflow regardless of the targeted platform. Whether it's on OpenShift, as you've seen earlier, or other Kubernetes platforms, or on premises, on your own hardware, or it's running somewhere in the cloud, you get the same consistent experience. All these built-in management features available in the big data clusters lead to a self-managed autonomous platform that enable you to focus on the application and getting valuable business insights out of your data. Together with the platform work and security enhancements enabled for the OpenShift support, the BDC deployment model and experiences were also enhanced. Our goal was to enable an experience where users can deploy BDC on the new OpenShift platform in an integrated manner. As you've seen in the demo, we added new built-in deployment profiles available out of the box with AZ Data with specific default values to target OpenShift environments. Both from BDC and OpenShift side, we provide the right tools, being APIs, command line utilities, or UX experiences that make it easier for you to manage things around this infrastructure. One such example I want to highlight in this sense is the OpenShift console. If you looked at the conference agenda looking for SQL Server Big Data Cluster sessions, you sure notice my colleague Melanie Quinn has a full session on administrating and managing SQL Server Big Data Clusters with platform agnostic capabilities that are available to you either out of the box or in external BDC tools ecosystem. But now I'm just going to give you a glimpse on what the OpenShift console is and what is available for you to do within the OpenShift deployment. To start with, you can see that OpenShift Container Platform Console is a web browser-based tool you can use to visualize or to browse and manage the contents of your projects. Depending on your credentials, you can have different permissions that are managed by the administrator. I'm actually logged in as an administrator user, so I should be able to manage all the artifacts in the cluster. Let's actually see what these artifacts are for a typical big data cluster deployment. We actually also documented all this for your reference in an article in our documentation, so feel free to use that as a pointer for better understand what happens during a big data cluster deployment and what are the components that are part of it. So looking through the console, we're going to start with the workloads here. Let me first filter down based on the namespace that big data cluster containers are deployed in. You can see what are the pods that form the big data clusters. We talked about earlier about the controller, SQL Server master instance, compute and data pools, and finally the storage pool that has HDFS and Spark. Also, as I've highlighted throughout the session, we will also deploy a set of applications for management and administration. You can see here the pods that are including the components that are doing metrics collection, like this metrics DC pod, or the controller watchdog that helps with upgrading the controller component itself, or the operator or zookeeper that are involved in the high availability configuration for SQL Server master instance in the case of the operator, and the name node and the Spark shared services for zookeeper. If you select any of the pods in the list, I'm gonna go with the controller here, you can also see high-level resource consumption, what are the containers, the logs, and other environment details for each one of these pods. Further along, just to summarize the workloads and to give you an idea, big data cluster deployment creates stateful sets that the pods we've seen earlier actually belong to. We see secrets for passwords and such. We see config maps for configurations as well as services. Here are the external services we were able to list out as endpoints earlier in the demo that you can use to connect to BDC applications like SQL Server master instance, the controller, or the gateway, that is the endpoint you authenticate against in order to submit Spark jobs or access HDFS. And let's not forget the storage. Here are all the persisted volumes and the claims that were created and bound to for the big data cluster deployment. You can also use the console for its monitoring and dashboard visualization capabilities. I really like the fact that the console includes a set of pre-built dashboards to track resource consumption at various granularity levels. Let's see if I select here the dashboard available for pods, resource consumption. You can see the CPU, the memory, or network metrics for each of the pods in the namespace we selected. Finally, yes, lots of concepts to grasp and to manage, but the tools available with big data clusters and OpenShift are making these tasks much easier, and hopefully this demo showed a glimpse of that. When it comes to administration capabilities, for all SQL Server releases throughout the years, SQL Server's commitment was to support mission-critical applications. Similarly, in big data clusters, the platform enables enterprise-grade secure access, high availability, automated upgrade operations, automatic logs and metric collections, and so on. Active Directory authentication is available for your secure authentication, providing an integrated security model that spans all services, including SQL Server, Apache Spark, and HDFS. We also have enhanced the security design of BDC to take full advantage of the OpenShift container platform. One of the most important enhancements in this regard is that containers are not running as non-root users as the default configurations when you deploy BDC. For in-depth details on the security design, please read the white paper we co-authored with SQL Server and Red Hat security teams that you have available as a resource in our documentation. It describes the design in details, highlighting what and why we require certain security policies when deploy BDC on OpenShift. You've seen in our demo how to integrate BDC with OpenShift from security perspective, how to create a custom security context, and what does that mean in the context of a BDC deployment. BDC also deploys additional components to manage high availability, management, and monitoring components. Every container inside BDC has a sidecar monitoring container that takes the logs in Elasticsearch and the monitoring telemetry into an InfluxDB database, so you can then visualize through Kibana and Grafana dashboards that are provided within the cluster out of the box. Now that I highlighted what are the specifics of deploying and managing BDC on OpenShift, I would like to also give you some insights into what we are planning next. Of course, we are continuing our collaboration with Red Hat to best support you on building your analytics solutions on this platform. So you're going to see that in one of the upcoming releases for BDC, we plan to close an important gap we currently have regarding the software stack, for example. We plan to deliver a new set of container images for BDC applications that are Red Hat-based images. We are also jointly supporting our customers to build their solutions. Some of them are pretty advanced with their solutions implementation, and we are going to work with these customers to share their use case publicly in the future so we all can benefit from that. We are also bringing our OEM partners into these conversations and continuously working with them on reference architectures. I included here a summary of these reference architectures that our partners published until now. Some of them, like the one you see here on HPE Synergy or Dell Unity VX, showcase how to scale BDC on OpenShift on their hardware. Ours and our partners' goal is to have a good mix of architectures that include different aspects of the stack, from the hardware to storage, host OS, Kubernetes orchestrator, and not to the least, various scaling factor, which is super important for this type of solutions. Thank you for all your attention. I hope you found this information useful. I know it was a packed session, but believe it or not, there is a lot more you can learn about big data clusters. Please leverage the other sessions here at DPS on big data clusters. My colleagues will go into more details on big data clusters from data engineer and data scientist personas perspective. I highly recommend watching this session. It is a great opportunity to see the value of BDC in action. You'll understand what type of workloads you can run on this platform, including SQL Server and Spark workloads, and what are the other capabilities available for you in this sense. A second session I would like to highlight is the one I mentioned earlier on administering and managing big data clusters. My colleague will go through multiple use cases in this sense, with lots of demos focusing on the built-in capabilities and the tools available to you either out of the box or in the external BDC tools ecosystem. There are many other resources we made available for you. Check out the latest SQL Server blogs and the BDC documentation to learn more about the improvements that we made available with the most recent cumulative updates, including the OpenShift support that I mentioned and other enhancements. SQL Workshops is another amazing resource. It has lots of good information, and more importantly, it has hands-on classes that you can take at your own pace, including a full information set for you on using big data clusters on Red Hat's OpenShift. Thank you again for joining. I hope I will see you again next year at DPS. And don't forget that I will stay around for at least 15 minutes or so to address all your questions and feedback.